A nonlinear load is an electrical load that does not draw a constant or sinusoidal current or voltage when connected to a power system. Its impedance changes with the applied voltage or current, resulting in a non-sinusoidal waveform. Examples of nonlinear loads include computers, electronic ballasts, light-emitting diode lighting, switched-mode power supplies, and arc furnaces. Linear loads, conversely, draw a constant or sinusoidal current and voltage, maintaining a proportional relationship between voltage and current. Common examples include incandescent light bulbs, resistors, and electric motors. Nonlinear loads create distortions in the power system waveform, known as harmonic distortion. These harmonics can interfere with other electrical equipment, causing problems such as increased power loss, overheating of transformers, voltage dips and surges, and equipment damage. To mitigate the impact of nonlinear loads, power system engineers use various techniques, including power factor correction. This involves installing capacitance banks to compensate for the lagging power factor caused by nonlinear loads. Another technique is using harmonic filters, which are devices that remove harmonics from the power system waveform. Isolation transformers can also be used. These isolate nonlinear loads from the rest of the system to minimize harmonic propagation. In summary, nonlinear loads are electrical loads that draw a non-sinusoidal current or voltage, contributing to harmonic distortions in the power system. Proper mitigation techniques are essential to prevent potential problems and ensure the efficient operation of electrical equipment. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency of the supply voltage. For example, if the supply voltage is 60 Hz, then the second harmonic is 120 Hz, the third harmonic is 180 Hz, and so on. Nonlinear loads generate harmonic currents that flow back into the power system. These harmonic currents can cause a number of problems, including voltage distortion, overheating of equipment, and interference with communication systems. Voltage distortion can cause malfunctions in sensitive electronic equipment. Overheating of equipment can reduce the lifespan of electrical components and increase the risk of fires. Interference with communication systems can disrupt radio and television broadcasts. To mitigate the effects of harmonics, various techniques are used. Firstly, harmonic filters. These filters are designed to block harmonic currents from flowing into the power system. They typically consist of capacitors and inductors that are tuned to specific harmonic frequencies. Secondly, power factor correction. Improving the power factor of a system reduces the amount of current that flows through the system, which in turn reduces the amount of harmonic distortion. Power factor correction is typically achieved by adding capacitors to the system. Thirdly, isolation transformers. These transformers isolate nonlinear loads from the rest of the power system, preventing harmonic currents from flowing back into the system. Fourthly, using harmonic mitigating transformers. These transformers are designed to reduce the amount of harmonic distortion that is generated by nonlinear loads. They typically have a special winding configuration that cancels out the harmonic currents. Fifthly, using active harmonic filters. These filters use electronic components to actively cancel out harmonic currents. They are more expensive than passive filters, but they are also more effective at reducing harmonic distortion. The selection of the appropriate mitigation technique depends on the specific application and the level of harmonic distortion that is present. It is important to consult with a qualified electrical engineer to determine the best solution for a particular situation. Consider a scenario where a commercial building houses numerous computers and electronic devices, all contributing to nonlinear loads on the electrical system. Without mitigation, the harmonic distortion could lead to overheating of transformers, voltage fluctuations affecting sensitive equipment, and even premature failure of some devices. To address this, engineers might install a combination of power factor correction capacitors to improve the power factor and reduce overall current, along with harmonic filters tuned to specific frequencies to trap and dissipate the harmonic currents generated by the nonlinear loads. Additionally, isolation transformers could be used for particularly sensitive equipment to prevent harmonic propagation. By implementing these measures, the building's electrical system can operate more efficiently, reduce the risk of equipment damage, and ensure a stable power supply for all devices. Nonlinear loads, such as variable frequency drives, or VFDs, and uninterruptible power supplies, or UPSs, are becoming increasingly common in modern electrical systems. These devices can generate significant levels of harmonic distortion, which can have a negative impact on the power grid. Harmonics are sinusoidal voltages or currents that are integer multiples of the fundamental frequency. For example, if the fundamental frequency is 60 Hz, the second harmonic is 120 Hz, the third harmonic is 180 Hz, and so on. Harmonic distortion is a measure of the amount of harmonic content in a waveform. Total harmonic distortion, or THD, is a common metric used to quantify harmonic distortion. Nonlinear loads generate harmonics because they draw current in a non-sinusoidal manner. This non-sinusoidal current creates voltage drops across the impedance of the power system, which in turn creates harmonic voltages. The harmonic voltages and currents can then propagate throughout the power system, causing problems for other equipment. Some of the problems that can be caused by harmonic distortion include, firstly, overheating of equipment. Harmonic currents can cause transformers, motors, and other electrical equipment to overheat. This can lead to premature failure of the equipment. Secondly, nuisance tripping of circuit breakers. Harmonic currents can cause circuit breakers to trip unnecessarily. This can disrupt power to critical loads. Thirdly, malfunction of electronic equipment. Harmonic voltages can cause electronic equipment to malfunction. This can lead to data loss, equipment damage, and other problems. Fourthly, interference with communication systems. Harmonic currents can interfere with communication systems, such as radio and television. This can degrade the quality of the communication signals. There are a number of ways to mitigate harmonic distortion. Some of the most common methods include, firstly, using harmonic filters. Harmonic filters are designed to block harmonic currents from flowing through the power system. They are typically installed at the point where the nonlinear load connects to the power system. Secondly, using power factor correction capacitors. Power factor correction capacitors can help to reduce the amount of harmonic distortion in a power system. They do this by improving the power factor, which reduces the amount of current that flows through the system. Thirdly, using isolation transformers. Isolation transformers can be used to isolate nonlinear loads from the rest of the power system. This prevents harmonic currents from flowing back into the power system. Fourthly, using harmonic mitigating transformers. Harmonic mitigating transformers are designed to reduce the amount of harmonic distortion that is generated by nonlinear loads. They typically have a special winding configuration that cancels out the harmonic currents. Fifthly, using active harmonic filters. Active harmonic filters use electronic components to actively cancel out harmonic currents. They are more effective than passive filters, but they are also more expensive. The best way to mitigate harmonic distortion depends on the specific application. However, in general, it is best to use a combination of different methods. For example, you might use harmonic filters to block harmonic currents, power factor correction capacitors to improve the power factor, and isolation transformers to isolate nonlinear loads. By taking these steps, you can reduce the amount of harmonic distortion in your power system and protect your equipment from damage. Let's delve further into the intricacies of mitigating harmonics caused by nonlinear loads, exploring the practical considerations and advanced techniques employed in real-world scenarios. Firstly, consider the impact of harmonic resonance. Harmonic resonance occurs when the inductive reactance of the power system equals the capacitive reactance at a particular harmonic frequency. This can result in a significant amplification of harmonic currents and voltages, exacerbating the problems caused by harmonic distortion. To prevent harmonic resonance, it is crucial to carefully analyze the power system impedance characteristics and design harmonic filters that avoid resonance conditions. This often involves using detuned filters, which are designed to shift the resonance frequency away from the dominant harmonic frequencies. Secondly, let's discuss the application of active harmonic filters, or OFF. Active harmonic filters are sophisticated devices that use power electronic converters to inject compensating currents into the power system, effectively cancelling out the harmonic currents generated by nonlinear loads. Unlike passive filters, which are tuned to specific frequencies, active harmonic filters can adapt to changing load conditions and mitigate a wide range of harmonic frequencies. They also offer the advantage of not introducing additional resonance into the system. Thirdly, explore the importance of proper grounding. Proper grounding is essential for minimizing harmonic distortion and ensuring the safe operation of electrical equipment. A well-designed grounding system provides a low impedance path for harmonic currents to flow back to the source, reducing voltage distortion and preventing equipment damage. It is crucial to avoid ground loops, which can create circulating harmonic currents and exacerbate harmonic problems. Fourthly, investigate the role of transformer connections. The type of transformer connection used in a power system can significantly impact the flow of harmonic currents. For example, delta-connected transformers can trap zero-sequence harmonic currents, preventing them from propagating throughout the system. Star-connected transformers, on the other hand, allow zero-sequence harmonic currents to flow freely. The choice of transformer connection should be carefully considered based on the specific harmonic characteristics of the loads being served. Fifthly, consider the impact of cable impedance. Cable impedance can play a significant role in harmonic distortion, particularly in long cable runs. The inductive reactance of cables increases with frequency, which can impede the flow of harmonic currents and create voltage drops. To minimize the impact of cable impedance, it is important to use adequately sized cables and minimize cable lengths. Sixthly, let's examine the use of harmonic studies. Harmonic studies are computer simulations that are used to analyze the harmonic characteristics of a power system. These studies can help to identify potential harmonic problems, evaluate the effectiveness of mitigation techniques, and optimize the design of harmonic filters. Harmonic studies are an essential tool for ensuring the reliable and efficient operation of power systems with nonlinear loads. When implementing harmonic mitigation techniques, it is important to consider the economic aspects as well. The cost of harmonic filters, active harmonic filters, and other mitigation equipment can be significant. It is crucial to perform a cost-benefit analysis to determine the most cost-effective solution for a particular application. In some cases, it may be more economical to reduce the amount of harmonic distortion generated by nonlinear loads at the source rather than trying to mitigate it downstream. To summarize, mitigating harmonics caused by nonlinear loads requires a comprehensive approach that considers the power system impedance characteristics, the harmonic characteristics of the loads, and the economic aspects of mitigation. By carefully analyzing these factors and implementing appropriate mitigation techniques, it is possible to ensure the reliable and efficient operation of power systems with nonlinear loads. Consider an industrial facility with numerous variable frequency drives controlling motors for various processes. These drives generate significant harmonic currents that can cause overheating of transformers, nuisance tripping of circuit breakers, and malfunction of sensitive electronic equipment. To mitigate these problems, the facility implements a combination of harmonic filters, active harmonic filters, and isolation transformers. The harmonic filters are tuned to the dominant harmonic frequencies generated by the drives, while the active harmonic filters provide dynamic compensation for changing load conditions. Isolation transformers are used to isolate sensitive electronic equipment from the harmonic currents flowing through the power system. By implementing these measures, the facility is able to reduce harmonic distortion to acceptable levels and ensure the reliable operation of its equipment. Moreover, understanding harmonic mitigation extends beyond simply applying filters or other devices. It involves a holistic approach that encompasses system design, load management, and ongoing monitoring. Firstly, consider the role of power system design. Designing a power system with inherent harmonic mitigation capabilities can significantly reduce the need for external mitigation devices. This includes using transformers with appropriate winding configurations, minimizing cable lengths, and optimizing grounding systems. Secondly, explore the concept of load management. By carefully managing the operation of nonlinear loads, it is possible to reduce the amount of harmonic distortion generated. This can involve staggering the operation of loads, reducing the load factor of individual loads, and using harmonic mitigating equipment within the loads themselves. Thirdly, discuss the importance of ongoing monitoring. Monitoring harmonic levels in a power system is crucial for identifying potential problems and evaluating the effectiveness of mitigation techniques. This can involve using harmonic analyzers to measure harmonic voltages and currents at various points in the system. The data collected from these measurements can be used to optimize the performance of harmonic filters and other mitigation devices. Fourthly, consider the impact of renewable energy sources. Renewable energy sources such as solar photovoltaic, or PV, and wind power can also contribute to harmonic distortion in power systems. Solar inverters and wind turbines often use power electronic converters that generate harmonic currents. It is important to carefully consider the harmonic characteristics of these devices when integrating them into the power system. Fifthly, examine the role of standards and regulations. Various standards and regulations exist that limit the amount of harmonic distortion that is allowed in power systems. These standards are designed to protect equipment from damage and ensure the reliable operation of the power grid. It is important to be aware of these standards and regulations when designing and operating power systems with nonlinear loads. Let's explore the different types of harmonic filters and their applications. Firstly, passive harmonic filters. Passive harmonic filters are the most common type of harmonic filter. They consist of capacitors, inductors, and resistors that are tuned to specific harmonic frequencies. Passive filters are relatively inexpensive and easy to install, but they can only mitigate a limited number of harmonic frequencies. Secondly, active harmonic filters. Active harmonic filters use power electronic converters to inject compensating currents into the power system, effectively cancelling out harmonic currents. Active filters are more expensive than passive filters, but they can mitigate a wide range of harmonic frequencies and can adapt to changing load conditions. Thirdly, hybrid harmonic filters. Hybrid harmonic filters combine passive and active filtering techniques. They typically consist of a passive filter that is tuned to the dominant harmonic frequency, along with an active filter that provides dynamic compensation for other harmonic frequencies. Hybrid filters offer a good balance between cost and performance. In summary, understanding and mitigating harmonics caused by nonlinear loads is a complex but essential aspect of modern power system design and operation. By adopting a holistic approach that encompasses system design, load management, ongoing monitoring, and the appropriate application of harmonic mitigation techniques, it is possible to ensure the reliable and efficient operation of power systems while minimizing the negative impacts of harmonic distortion.